page 87, 5-9. So between today and tomorrow, we should feel pretty prepped for this two-part test that we have Thursday and Friday. But on page 87 says a random sample of 25 cheeseburgers is ordered. So what did I say now? If we're under 30, what test are we going to start using? T, yes. So we're okay saying 25 because we have the T table now to use. It says order specific, my friend, good to see you. A specific fast food restaurant average 820 calories with a standard deviation of 35. We wish to use the confidence intervals to evaluate this data. So number one, we want a 90%. We know we have a sample of 25. We know we have a mean of 820. And we have a standard deviation of 35. Hello. Good to see you. All right. So, because this is low, this has to be the T distribution now. And you can find that on our best buddies and pals. And make sure you have this out so I can give you the points for it. Fill in what you need to fill in. Decimals. All right. So, in order to find the T distribution, under functions, roll down. All right, so when it says T distribution, it goes automatically to something underneath that says enter degrees of freedom. So we have a sample of 25 cheeseburgers. What's my degrees of freedom? 24, yeah, it's always one less. Everyone should get that one right. Okay, so this is what our T distribution looks like. Looking good. So remember our T distribution, we have to use this for our margin of error. We have T times S over the square root of N. Okay, so when we do the T distribution, we have to figure out what T is. So that's going to be where we use T distribution and then degrees of freedom and then inverse CDF, period, inverse CDF. And then this here is the halfway to 100. So if we were using 90%, what are we plugging in here then? Hey, good to see you, brother.
So slow.
So that should be 95 or 0.95 because halfway from 90 to 100 is 95. All right, so let's take a look what Desmos will offer us. So we're going to go period. And then we're going to find inverse CDF. Inverse CDF. And we're going to plug in 0.95. So that's our T value. So that's representing the same thing as the Z-score, but using a T distribution. So 1.71. So we'll have 1.71 times S, our standard deviation, times 35. So that's times 35 over the square root of our sample size. So that's going to become 1.71 times 7. So let's see, that's 7, 9, carry the 4, that's 11.97. All right, so now we're ready to, our 11.97, we're ready to go and start fixating this. So we're going to go 820 plus or minus 11.97. And let's see, that's 12, 8, 8. What's 820 minus 12? 808, 807.03 to 831.97. Okay, so let's see if we have everything here. The critical value, this is our critical value. So that's the answer to 1. Calculate the margin of error. Margin of error is right here. Hello. Calculate the confidence interval. Or actually, this is our margin of error here, MOE. And then this will be number 3. That's our interval. And then interpret the meaning of this. We are 90% confident that if we did another random selection of 25, we're on page 87, friends. If we did another random selection of 25 of our hamburgers or cheeseburgers, our calories for those cheeseburgers would be between 807.03 to 831.97. Okay, so if someone said, hey, all these cheeseburgers have an average higher than 800 calories, is that a legitimate thing to say? Yeah. If we were to say, hey, all our cheeseburgers have above 820 calories, is that a legitimate thing to say? No, why not? It's inside of our confidence interval. Good. Cool. All right, do we feel comfortable with cheeseburgers? We're happy? I like cheeseburgers, so. All right, number down below. It says a random sample of 10 homes in the Sunnyside neighborhood in Miami showed an average home value of 410,000, standard deviation of 100,000. Okay, so we have a sample of 10. So what do we have to use because it's a sample of 10? Do we use normal or T? I talk to myself again? T, because it's less than 30. It's also T because we're using our sample standard deviation. Okay? So there's two things that pertain to using a t-test. If you're using the sample standard deviation and or you have a sample less than 30. So kind of note that. Okay, so we want to produce a 95% confidence interval. So we have a 95 here. We have a 99 we'll do over here. So we'll answer both those questions. Okay. So this will be, excuse me, T times standard deviation over the square root of the sample. Okay, so we have to find our T. So that's going to be T distribution. Degrees of freedom in this one is going to be 9 because that's one less, times inverse CDF. And halfway to 100 from 95 is 0.975. Oh, it just went on me. No. Let's see if I change a pen. I was so close to having this problem done and it goofed up on me. Thanks for tolerating my bogus technology. All right. So again, we have a sample of 10. An average of 410,000. Standard deviation of 100,000. I don't know why this thing is, other than it is outdated or something. So again, if we're looking for our 95% confidence, we're going to have our T distribution times our standard deviation. You got to be kidding me. All right, well. Oh, let's load. Let's go to Desmos. All right, so I'm going to change our degrees of freedom here to 9. And our confidence interval, it's a 95%, so we're going to change this to 0.975. So the 2.26 times our standard deviation, which is 100,000. I think I have too many zeros there. that right? That's a million. That's 100,000. Divided by square root of our sample size, 10.
Hey, how'd you get going? Oh, wait.
So our margin of error is going to take place, or for this confidence interval, we're going to go 410,000 minus 71,467.48 and 410,000 plus 71,467.48. So we will be 90% confident. We are 95% confident that if we did another random selection
Merry Christmas.
Oh, well, thank you.
My mom says my dad might have opened it, but she stopped it before he got into it. So.
Well, thank you. Love it. So we are 95% confident that if we were to select another 10 homes in this Sunnyside neighborhood in Miami, that we would find our home values between $338,532.52 and $481,467.48. And then if we change that to our 99% confidence, this is going to become 0.995. Okay, so that's going to spread things out even further. So then if I change this here to 3.25, oops. So then it's going to range out further. So I'm going to go, this will go up to 102,774.02 and 102,774.02. So now we would be 99% confident for number 6, 99% confident that if we were to select another 10 homes in the Sunnyside neighborhood in Miami, that our house prices would go between $307,225,098 or $307,225.98 to $512,774.02. Okay, so the 99% confidence makes that range a lot broader. In general, what do problem 5 and 6 say about what happens to a confidence interval as confidence levels rise? Confidence level rises, that basically means that I'm spreading out my interval a lot more. Okay, so where does the comfortable confidence interval lie? I'm not quite sure. I just know that if you know what you're looking at, you can make a better judgment call based on yourself. Okay, this second one basically means we have a 1% chance of something falling outside of that window. The other one meant we had a 5% chance of it falling outside of that window. All right, page 88. Educational researchers wish to find an average ACT score of students at a particular school. A random sample of 10 students produced an average ACT score of 20.2 with a standard deviation of 6.8. So this means we have to use a t-distribution for two reasons. We have the sample standard deviation, and we have a sample size less than 30. Okay, so that was the answer to number 8. Briefly explain why t and not z is appropriate here. Sample standard deviation we're using. We're not given the overall standard deviation, and we have a sample size less than 30. Number 9, calculate the confidence interval on a 50% confidence. Okay, so I could still use this. My degrees of freedom is 9 because my sample size is 10. I want a 50% confidence interval. Okay, what is halfway to 100 from 50? Yeah, 0.75. Okay, so then I'm going to change this to my 0.70. I'm going to change this to my standard deviation is 6.8. And that's still going to work. So now my standard deviation with a 50% confidence interval, I'm going to, did I do that right? 68. Oh, I made a mistake. That should be 6.8. 6.8. So because we're only 50% confident, we're going to be 1.51 above and 1.51 below. So if I delete this, so I go from 20.2 plus 1.50, and then change this one for 20.2 minus 1.5. So I am 50% confident that if we selected another 10 students from this educational research on ACT scores, I'm only 50% confident that my scores will fall between 21.7 and 18.7. That means I have a 50% chance of it not happening. Okay? So the confidence interval, when it gets lower, I mean, we have a much bigger chance that it might not happen. Consider your answer number 10. Why is the confidence interval 50% not used often? Because you have a 50% chance that you will fall within your confidence interval, and you'll have a 50% chance that it will fall outside of it. And then it says calculate a 99.9% chance. Okay, so let's go halfway to 100 here. What's halfway to 100 if you're at 99.9? 0.9995. Holy cow. Okay, so that's going to change this to 4.78. Okay, so then that spans 10.2. And then what I'm going to do is I'm going to change this from 10.27 and this to 10.27.
Wouldn't it just be 0.9?
Well, they wanted 99.9.
Oh, okay.
And so that becomes 99.90. So make the point, or the 0.90, 0.95.
Okay, I thought it was 99. That's fine.
Yeah, oh, okay. All right. So, friends, if we were to go select another 10 random students, we are 99.9% confident. So we have a 0.1% chance of this event not happening. But if we selected 10 random students again, we would find that their scores on the ACT would range between a 9.93 and a 30.47. Now, obviously, ACT is a whole number they give you, but that's just basically the fixation of it. Okay, interpret this confidence interval. Again, we're 99.9% sure that if we select 10 more students, that they fall in between the range from 9.93 to 30.47. Okay, consider an answer number 13. Explain why a confidence interval at 99.9 is not used often. Okay, I am so broad on my scores. Okay. You know, if I were to say, hey, I'm 99.9% sure that I'm going to pick a random 5 students out of this class that have hair, we're like ridiculous close because we all have hair minus stirrups, few hairs. Okay? All right, you guys ready for the very last unit for me to talk about? Let's do it. Friends, I'm now going to be on page 21. You with me? All right. So the meaning of a confidence interval. Okay, meaning of a confidence interval. If you go down about 2/3 of the way down, you have this weird looking vertical lines up and down. So what that basically is that is a confidence interval for 100 samples. So we have 100 samples where we had selected 3 people at random, okay? So notice that confidence interval that's posted there is basically where everything would fall. And if you look at the 4th one in, and then you look at the ones that are like a different gray line, they have a circle dot rather than an X. Those are the ones that fall out. So it says, as you can see, most of the confidence intervals successfully capture the population mean of 5. Those in red, the ones in red that have the star, or with the dots in the center rather than the X's, failed to capture the population mean. Some intervals are wider and some are narrower, which would be indicative of varying sample sizes used. The larger sample sizes would yield shorter intervals. Okay, so what that means is, and I've said this over and over, if I had, say, a population of 10 million people that I'm trying to take a random sample of, and I go and randomly select 10 people, and then 10 people, and then 10 people, and I'm trying to figure out like their average income, if I keep doing a random selection of 10 people, and I did it 100 times, this is what the graph might look like, where we have all those vertical lines, where there is a chance that we would get something that would fall outside of our sample size, okay? And this one's based on a 99% or 95% confidence interval, and it changes as you go through it. Backside says, so 95% confident means 95 out of 100 random samples will produce confidence intervals that capture the population mean. It is expected some intervals will fail to capture the population parameter. This is akin to rolling two dice. It is expected that every so often, the unusual result of double sixes will occur as a byproduct of randomness. So, guys, if you roll two dice, the most likely number to come up when you add the top numbers is a 7. Okay, the least likely is 2 and 12. But it is possible that you could roll a 2 or a 12 on dice. And if I gave you all dice and you rolled each of those dice 10 times and gave you your calculations, we would basically get very close to get it to 7. We'd probably have a standard deviation depending upon how often we did it, but we'd have a standard deviation that would be pretty close to maybe 1. So it would go between 6 and 8. Okay, and it depends on our confidence interval when we do it. Okay, a question arises at this point. Is it okay to use the language of probability to interpret what it means to be 95% confident? Consider the possible interpretation. Okay, this is about halfway down. There's a 95% chance that our confidence interval captured the population mean. While this statement might be appealing, it treats the population mean as a moving target and the confidence interval as the constant. The confidence interval is simply one of infinitely many confidence intervals that could be constructed. Another researcher might select a different random sample and produce completely different interval. Random variables occur everywhere, and we often assess their probabilities. We might wish to use the chance of a thunderstorm tomorrow. We might wish to know that the probability that I will flip a coin 10 times that I get all heads. We might want to know who will win the World Series in baseball this year. Using probability language is acceptable when the situation with many possible outcomes. But the population mean is fixed. It isn't moving. It's considered as inappropriate to use the probability language to discuss the probability of something that is fixed, even when it is unknown. Therefore, the best, most accurate way to interpret a confidence interval is the way we have been doing thus far. 95% confident means 95 out of 100 samples will produce confidence intervals that capture the population mean. Okay, that's not even, if I did 99% confidence, 99 out of 100 random samples will produce confidence intervals to capture the population mean. If I have a 50% confidence interval, means 50% of every 100, or 50 out of every 100 samples will produce confidence intervals that capture the population mean. So just kind of make sure your language, note down at the bottom of page 22, that 95% confidence. Using that language is a very acceptable language to use for statistics. Okay? So, I think you guys are ready to do page 89 and 90. We'll go over that tomorrow, and we'll also do some review as well. Okay, but that's what I got for you.